Section 3.8 has to do with taking the derivatives of logarithmic and exponential functions. And so we're going to talk about the rules to take the derivatives of these functions when we work through them. We're going to start with the logarithms. And the nice thing about the logarithms and the exponentials is if the base is e, that's the easy one. That's why we really even talk about e so much. There's some fundamental properties of its derivative that make it interesting. But the ln of x, that's an L, not an I, it's not in x, but ln x. The natural log of x is the log base e. So when you see ln of x, what ln of x literally means is the log base e of x. And when I take the derivative of the natural log of x, I get 1 over x. That's the trick. The derivative of the natural log of x is 1 over x. But if the base is something other than e, then it doesn't work out so nice. So let's look at what happens when the base is something other than e. Here the base is the general base b, whatever that number is. B could be 2, b could be 1/2, b could be 7. But if I have the log base b of x, I can use the change of base formula to rewrite it in terms of the natural log of x. Remember, the change of base formula says the log base b of x can be written as the natural log of x over the natural log of the base. This is just from the change of base formula. So these two things are exactly the same because of the change of base formula. But I can rewrite ln of x over ln of b as 1 over b times the natural log of x. And if you think of the natural log of x as being over 1, you can see that. 1 times ln is ln x. 1 times ln b is ln b. But the natural log of b is going to be a constant. It's going to be a number, like 1 over the natural log of 2. So when I take the derivative of f of x, then that 1 over ln of b is a constant, so it sticks around. And the derivative of the natural log of x gives me the 1 over x. So when I take the derivative of a log of another base, then it's 1 over the natural log of that base times 1 over x. Notice when the base is e, the natural log of e is just 1. That's why this doesn't show up when you see an e. This turns out to be 1 over the natural log of e times 1 over x. 1 over the natural log of e is just 1. So this part here goes away. It turns out to be the number 1 when the base is e. That's why we didn't see it before. So let's look at some examples of this. For example, the log base 7 of x. You can either remember the derivative right off, 1 over natural log of 7 times 1 over x. Or, if you wanted to, you could rewrite this using the change of base formula, which is 1 over the natural log of 7 times the natural log of x. So when I find the derivative of this thing, 1 over natural log of 7 is a constant. That was the natural log of b in the general case above. And the derivative of the natural log of x is 1 over x. And that's it. So when you have a log, you have to divide by the natural log of the base. Here's another example. The log of base 2/3 of x. One way to do this is to just write down the derivative because you memorized how to do it. 1 over the natural log of the base, 2/3, times 1 over x. But if you wanted to do it with the change of base formula, that's the ln of x over the ln of 2/3, which is 1 over the ln of 2/3 times the ln of x. The natural log of 2/3 is a constant, so that sticks around. The derivative of natural log of x is 1 over x. So if you forget the formula, you can use the change of base formula to help you remember these. What about the chain rule with logarithms? Well, let's look at what happens when I have a natural log. Remember, the natural log is log base e. So it's already in terms of natural log. I can already find the derivative. But notice when you use the chain rule, it's the stuff in the parentheses that take the place where x used to be. In this case, it's the argument of the natural log. So when I find the derivative of this, I have to draw a box around the parentheses. And then I take the derivative around the box. The derivative around the box leaves the box alone. And I take the derivative of the natural log of x. Well, what is the natural log of x? It's 1 over x. So the derivative around the box is 1 over the stuff that's in the box. Remember, the derivative of ln of x is 1 over x. the derivative of ln of a box is 1 over the box. This is the derivative around the box. But then you got to multiply by the derivative inside the box, which is 6x minus 7. So when we're all done, this is in the box. So when we're all done, the stuff that goes inside the box is on top, and the stuff the derivative of inside the box goes on top. The stuff in the box goes on the bottom. This is a general formula. When you're using the chain rule with a natural log, the argument goes in the denominator. The derivative of the argument goes in the top, because that's multiplying by what's inside the box. So when I take the derivative of the natural log, the derivative goes on top, the argument goes on the bottom. So we can try an example again. Here I have that 4, which is a constant. And so when I think about this, I could use the change of base formula. Natural log of x squared minus 1 over the natural log of 3. And 4 and the natural log of 3 are constants, and I'm left with the natural log of x squared minus 1. And again, to find the derivative of this natural log, I need a box. Or I could remember the property. The 4 over natural log of 3 is a constant, so it sits around. The derivative of the natural log of x squared minus 1, the argument, x squared minus 1 goes on the bottom. That's the derivative around the box. The derivative of x squared minus 1, 2x, goes on top. So again, when we use the chain rule on these logarithms, a lot of times you can rewrite it with a change of base formula to help you see what happens when it's just a natural log. And then you can remember that the argument goes on the bottom and the derivative of the argument goes on top. Well, here's a tougher one for the natural log. Natural log, or log base 5 of the square root of 9x to the 4th plus 9x. There is a faster way to do this than I'm about to do it, and the faster way is going to come below, logarithmic differentiation. That makes it quicker. But let's do this one the long way. First, I'm going to rewrite it as the change of base formula. 1 over the natural log of 5 times the natural log of 9x to the 4th plus x, all to the 1/2 power. Because that's what the square root is, the 1/2 power. Now there's a log property that says I can bring the 1/2 out front, but that's something we'll do in a moment. If we take the derivative right now, 1 over the natural log of 5 is a constant. And to find the derivative of the natural log of something, the argument goes on the bottom, 9x to the 4th plus x to the 1/2. The derivative of the argument goes on top. So let me go over here to the side and just find the derivative of 9x to the 4th plus x to the 1/2. Notice that's another chain rule. The derivative around the box well, the 9x squared plus 4x, 9x to the 4th plus x, stays inside. The 1/2 comes out front. The power becomes negative 1/2. That's the derivative around the box. The derivative inside is 36x to the 5th plus 1. So you could simplify this if you'd like to. If you simplify this, you get that the derivative is, on the top I have 36x to the 5th plus 1. On the bottom I have 2 times the square root of 9x to the 4th plus x. And so that's what's going to go up here. 36x to the 5th plus 1, and 2 times 9x to the 4th plus x to the 1/2. Now I can put this together to make it look nice, but as it sits, it's okay. It shows me you know the process. The argument goes on the bottom. The derivative of the argument goes on top. You could rewrite this, however, as 1 over the natural log of 5 times 36x to the 5th plus 1 over 2 times 9x to the 4th plus x. You could have simplified it further if you wanted to, although it's not required. With these derivatives, a lot of times, I'm just happy to see that you've taken it properly, in the right way. But that one's a really nasty one because you had to use the chain rule when you found the derivative of the argument to put on top. Logarithmic differentiation is a way you could have made that last one faster. When you do derivatives with logarithms, the idea is to expand it out with these log properties. Make one log into a whole bunch. And then find the derivative of the whole bunch, because that's easier. And so here are the three properties. The first property says, if you multiply two things inside of a log, don't notice the base, doesn't matter what the base is. If you multiply two things inside a log, it's like the log of the first thing plus the log of the second thing. These are coming from the power rules, the way you put powers together. The log base b of m divided by m is the natural log of the top minus the natural log of the bottom. So when you multiply in a log, you can write 2 and add. When you divide in a log, you can write 2 and subtract. When you take the log of something to a power, you can take that power and write it out front. So you could have done that property, that derivative we just did, by taking that 1/2 and multiplying out front. And then I would have had 36x to the 5th plus 1 over 9x to the 4th plus x if I'd have done that. I could have rewritten this as 1 over ln of 5 times 1/2 natural log of 9x to the 4th plus x. And that's that third power rule. It says if I'm raising something to a power, I can write the power in front of the log. This is not taking any derivatives, it's just rewriting it. So I could have rewritten this power in front of the log. And then I could have found the derivative. The derivative would have given me 1 over 2 ln 5. On the bottom, 9x to the 4th plus x. On the top is the derivative of that. And that's exactly what I got doing it the long way. I just put the 2 over here instead of by the natural log of 5. So notice, this just makes the derivatives faster to find, but you have to know the properties. Adding inside a log is like, or multiplying inside a log is like adding 2. Dividing inside a log is like subtracting 2 logs. And you can take the powers and write them out front. So I'd like to take the derivative of this using natural logs. You don't have to. You could have taken this derivative using the quotient rule or the product rule. But I can rewrite this using natural logs. Well, if I want to use the log properties, I have to put logs on both sides. So I have the natural log of y equals the natural log of x plus 1 to the 10th. Over 2x minus 4 to the 8th. I just took the natural log of both sides. But now I can expand this right-hand side. I have the natural log of y equals, well, I'm dividing two logarithms. So I can write the log of the top, x plus 1 to the 10th, minus the log of the bottom, 2x minus 4 to the 8th. That's the second log property that you can just see up here. The log of two things divided is the log of the first minus the log of the second. And I can also use property 3. Property 3 says if there's a power, you can write the power in front of the log. So I get the natural log of y is 10 natural log of x plus 1 minus 8 natural log of 2x minus 4. That was property 3 I used. It let me take these powers and write them in front of the logs. Now I can take the derivative. If I want to find the derivative of the natural log of y, well, the argument goes on the bottom. So y goes on the bottom. The derivative of the argument, which is dy dx, or y prime, goes on top. So the argument y goes on the bottom. The derivative of the argument goes on top. 10 is a constant. The derivative of the natural log of x plus 1. X plus 1 is on the bottom. The derivative of x plus 1, which is 1, is on top. 8 is a constant. Natural log of 2x minus 4. 2x minus 4 goes on the bottom. The derivative of 2x minus 4, 2, goes on top. And so I end up with y prime over y equals 10 over x plus 1 minus 16 over 2x minus 4. That's y prime over y. Now I want to solve this for y prime, because that's what the derivative is. So that means I have to multiply the other side, 10 over x plus 1 minus 16 over 2x minus 4, times y. I took this y and multiplied it to the other side. Let me write this in 2 steps. I have y prime over y equals 10 over x plus 1 minus 16 over 2x minus 4. I multiply both sides by y, and I get y prime is 10 over x plus 1 minus 16 over 2x minus 4 times y. But I know what y is. Y was what I started with. So my final answer is y prime equals the stuff in parentheses, 10 over x plus 1 minus 16 over 2x minus 4, times y. And y is x plus 1 to the 10th over 2x minus 4 to the 8th. Notice a lot of times when people take the derivative of the natural log of y, they forget that it's y prime over y. But notice this is actually a fairly quick way to take the derivative. You don't have to use the product rule or the chain rule as much. It's a little bit faster. But that you can leave it just like that. You don't have to simplify it any further. But note that I replaced y with what y is equal to. Well, there are actually two more I wanted to look at. But let's just look at this one here. The other one was a product rule anyway. This one here, I have to use natural log for. Whenever I have variables in the base and in the power, you have to get that x out of the power. This one above, I could have gotten away with just finding the derivative normally. I didn't need to take the natural log of both sides. I could have used the quotient rule and found the derivative, because all the x's are in the base. They're just numbers in the powers. It's not mixing them. But this one here has x's in the base and in the power, so the only way to do this is by taking the natural log of both sides. So this is really y equals x sine of x. And I have to take the natural log of both sides so I can make that sine of x come down. Remember, if I have natural log of y is the natural log of x sine x, I can use property 3 of logarithms to bring the sign in front of the natural log. And so I get the natural log of y is x. Natural log of y is bring down the sine of x, and what you're left with is the natural log of x. The sine of x comes out front, ln is left all alone. That's property 3. Notice I haven't taken any derivatives. I took the natural log of both sides, then I used the third property to bring sine out front. But now I'm going to find the derivative. And when I find the derivative, on the left side, the natural log of y, when I take the derivative, y, the argument goes in the bottom. The derivative of the argument, y prime, goes on top. When I take the derivative of the right side, I have to use the product rule, because I'm multiplying two functions of x together. U is the sine of x, v is the natural log of x. The derivative of sine of x is cosine of x. The derivative of natural log of x is 1 over x. So now I can use the product rule. It's uv prime, sine of x over x, plus vu prime, ln of x times cosine of x. But just like before, I have to multiply that y over, so I get y prime as sine of x over x, plus natural log of x times cosine of x, all times y. And I can multiply through. I can write down what y is, because I know what y is. So I get that y prime is the sine of x over x, plus the natural log of x times cosine of x. And then instead of y, I can write what y is. Y is x to the sine of x power. That was y originally, that was given to me at the beginning of the problem. So logarithmic differentiation means take the natural log of both sides and find the derivative. Use the log rules to help you. When you have functions that have variables in the base and the power, this is the only way to do it. But it's also a useful technique if you have problems that would require a lot of dividing and quotient and chain rules. But these you have to use it on. So now I want to just spend a little bit of time talking about how to find the derivative of exponential functions. We know the basic exponential function is e to the x. So the derivative of e to the x is e to the x. And we learned that before a couple chapters ago. Notice when you take the derivative of e, you get back what you started with times the derivative of the power. And that's coming from the chain rule. But now the question is, what do I do if the base is something other than e? Well, you can use a formula. I can rewrite 2 to the x as e to the natural log of 2 to the x. And the reason I can do that is because e and natural log are inverses of each other, and when I raise the e to the natural log power, they erase each other, and the 2 to the x falls down. But notice I have a natural log in here. So that means that by property 3, that x can multiply in front of the natural log. And now I can take the derivative. The derivative of e to a power, you get it back, e to that power, times the derivative of the power. Well, the natural log of 2 is a constant, so it sits around. The derivative of x is just 1. So this is the natural log of 2 times e x ln 2. And then we can go backwards. We can put it back together. Natural log of 2 times e natural log of 2 to the x. I'm just going backwards from the way I just went. E to the natural log of 2 to the x is just 2 to the x. That's the trick in general. In general, if you take the derivative of a base to the x power, you get back what you started with times the natural log of the base. When you take derivatives of logarithms, you divide by the natural log of the base. When you take derivatives of exponential functions, you multiply by the natural log of the base. You don't have to go through this process every time. You can just remember the pattern. Here's how it works, though. If I have b to the x, I can do all that funny stuff that I did, and I end up with this, which turns out to be b to the x times the natural log of b. You get back what you started with times the natural log of the base. So let's look at this first one, 5 times 4 to the x. When I find the derivative, 5 is a constant because there's no variables in it. The derivative of 4 to the x, you get back what you started with times the natural log of the base. Notice if the base is e, you get the natural log of e, which is just 1. That's why you don't see this when you're taking derivatives of these. Back what you started with times the natural log of the base. And let's look at one more of these. Here's 2 exponential functions. Well, one's a polynomial, one's an exponential. But if I want to find this derivative, I need the product rule, because both of these are functions of x. So in this case, my u would be x cubed, my v would be 3 to the x. The derivative of x cubed is 3x squared. The derivative of 3 to the x, you get back what you started with, times the natural log of the base. So now I can use the product rule. uv prime is x cubed times 3 to the x times the natural log of 3. That's uv prime. vu prime is 3x squared times 3 to the x. And there's lots of things you could do to simplify this, but that's good enough for me. It shows me if you understand the process and how to solve these problems.